Hi, and welcome to a video that's about where these formulas come from, and these are formulas for finding the length of a curve. The first formula is if you were looking at a curve that is a function defined in terms of x, and you've got your limits of integration defined as x values. And the second one is if x is written as a function of y, and you're going from a lower limit and an upper limit that are defined in terms of y. So we're going to talk about where these two things come from, and in order to do that I want to look at a curve. If you look at this curve, if we connect the endpoints we get a really poor estimate for the length of this curve. However, if we maybe do this, maybe use two segments, our estimate for the length of the curve would be better if we could find the length of this segment and the length of this segment. If we got more curves, you can see the more segments we use, the better it's going to be for an approximation. So let's go back to here and let's think about how do we get the length of this red segment. Well, if you think in terms of the Pythagorean theorem and the distance formula, we can use the Pythagorean theorem once. Here we would use it twice. Here are 3, 4, 5, and so forth. So this formula, or these two formulas, really come from the Pythagorean theorem. So let's talk about that a little bit. Let's look at a curve that is defined in terms of x. And we're going to look at that curve from A to B. Now, if I connect these two endpoints, I can draw a triangle. And that right triangle is determined by the Pythagorean theorem. So if we call this the change in x, or delta x, and this the change in y, delta y, we can call this the length. Let's call that delta s. And if we go through our Pythagorean theorem, as you guys all know, we know that delta s squared is going to equal delta x squared plus delta y squared. Okay, so you can start to see what's going on here. You've got the square root, you've got the squared, but we don't see the one here over here. Well, let's think about what happens. We're not going to just use one triangle to approximate the length of the curve from A to B. We're going to use a lot of triangles. In fact, we're going to use so many triangles that we're going to get an accurate length for the curve, and that would mean we would have to use infinity triangles. So if I want to use infinity triangles, I need to represent this length as a length of any given triangle that is within the infinity triangles that I've created, or that I will create. So these sub i's represent the ith triangle in the infinite sequence of triangles, and we're going to start with one triangle, so we're going to let I equal 1 to start with, and by the time we get to the end here, I would equal n, because we're going to have n triangles instead of just one. So we're going to sum up all of those triangles from I equal 1 to I equal n. And that means we're going to sum up all those lengths. And that means we're going to sum up all the things that are equivalent to the length. And when we get to here, this is really starting to look like a Riemann sum. In fact, if I sum up all of these lengths, I need to let the limit of delta x go to 0. If we do that, if we let the limit of delta x go to 0, then what I'm actually doing here is creating an infinite number of infinitely small triangles, and I'm adding up all of their hypotenuses, and we're going to get an exact value for this delta x with s, which is the sum. All right, so if we look at this, the problem with this is it's not yet a Riemann sum. Remember, a Riemann sum has to look like the limit as n goes to, delta x goes to 0, and we need an f of some c sub I times a delta x, where this is kind of like your height, and this is kind of like your width, and you're going to equal an area. Because remember, when we do Riemann sums, we add up an infinite number of infinitely small rectangles, so we need a height and a width. We don't have a delta x here, so let's go ahead and multiply by delta x. If you multiply by delta x, you have to do an equivalent inverse operation, so we need to divide by delta x. Those two things are going to cancel each other out. All right, let's simplify this a little bit. So I'm going to start to ignore the left-hand side a little bit and just focus on the right-hand side. We've got the limit as delta x goes to 0 of the sum of this thing. All right, so I've rewritten this and I've put some V's on here to also show that we're at the ith triangle in the sequence of triangles that we're adding together. And I've also put this denominator inside the square root, and that's why this is turned into a delta x sub I squared, because I have put it under the radical sign. So now let's simplify this a little bit and see where that gets us to. All right, now if you look at this, you can see that this is going to turn into 1. This is going to turn into delta y over delta x quantity squared, which, if you think about it, that's pretty much the same as dy over dx quantity squared if we were going to write it in terms of calculus. So let's take this Riemann sum and now let's transform it into a calculus integral. And remember, we're adding up all these triangles. If we go back to our picture, we're starting at A and we're ending at B. So when we write this in integral form, our integral needs to start at A, end at B. This delta x sub I turns into our dx. All of this stuff turns into our function, which is going to be the square root of 1 plus, this we've already talked about, turns into dy dx quantity squared. And we have our formula. This represents our, if we go back up here, it represents our delta s, or delta s sub I, or the sum of the infinite number of hypotenuses if we were to make an infinite number of right triangles. So we have effectively figured out a formula using the Pythagorean theorem and calculus to get the exact value of the length of that curve, and that would be what we end up right here at the end. You can do the same thing in terms of y, but we're not going to repeat the process. So I hope this makes a little more sense. When you're thinking about this formula, think about the Pythagorean theorem. This really right here looks a lot like the square root of a squared plus b squared, but because we had to do some algebra up here with the delta x sub I so we could get it in terms of a Riemann sum form, we had to modify that a little bit. All right. There are several examples where we use this formula so you can see how it's implemented. Please continue watching those, work through the handout that you have, and let me know if you have any questions. Good luck.